This is our final lesson in a series that I did with the grandkids, in which together we built a metal detector, as they learned principles of physics that made it work. In our previous lesson, we saw how a radio frequency oscillator works as a key component of a metal detector. In that demonstration, we first tuned an AM radio receiver to a distant radio station. Then we tuned our RF oscillator as close as we could to that same radio frequency. And we heard how those radio signals interact, or heterodyne, as we say in the radio business, by generating an audible tone, the beat frequency between those two radio signals. And as we brought a piece of metal in proximity to the large tuning coil, the frequency of the radio signal that our oscillator generated shifted, and we could hear that shift by the changing pitch of the resulting beat frequency. Now we want to grow this circuit so that it does not depend on that AM radio receiver. So the next stage in building our metal detector is to construct a second RF oscillator to replace the radio station signal. It's identical to the first oscillator that we built by simply using the other half of the dual operational amplifier chip that is already on our snap circuit board. For the second oscillator, we're using the same tuning coil that we originally used in our first oscillator back in lesson 3 and hook it up with an identical variable capacitor. You'll find a link for purchasing spare parts for snap circuits in the description of this video. It's a good idea to test each oscillator separately to make sure that they both work independently and that we don't have any bad components or bad connections. To do that, I disable one of the oscillators by disconnecting its positive feedback loop. I turn on the power and see if I can pick up the other oscillator on my AM radio receiver. Then I disable that oscillator and run the same test on the first one. Now let's try them together. First, tune the receiver to a dead spot on the dial. Tune one oscillator to that frequency to quiet some of the static. Then tune the other oscillator until we hear the beat frequency. Now let's test it with a piece of metal near the detection coil. Now there's a little problem with this circuit as we designed it. I found that when I tune the two oscillators to the same frequency, they quickly lock in on each other so that the resulting beat frequency is 0. That locking effect makes it more difficult to change the tuning of the detection coil with a piece of metal. We want the circuit to be more sensitive than this. Why are the two oscillators locking in on each other this way? Perhaps you've seen a demonstration of a bunch of metronomes set to the same rate on an unstable table surface. In a short time they fall into sync with each other as the oscillation of each metronome feeds through the vibrating table surface to every other metronome. The same thing is happening here with our two radio frequency oscillators. The two operational amplifiers are built into the same integrated circuit, the same chip. A bit of the signal from each op-amp is feeding across the shared powered circuit to the other op-amp, and just like our metronomes, they fall into sync with each other. In the case of our metronome demonstration, if we made the table surface more stable, that would dampen the crossover effect from one metronome to another. And we can do the same thing for our two oscillators. If we put a radio frequency bypass capacitor, say 0.01 microfarads, across the power leads of our op-amp chip, that would filter out some of the signal bleed-through in the power circuit. We could go even further in eliminating this phase locking effect altogether by using separate integrated circuits, separate op-amp chips, one integrated circuit for each oscillator, and fielding the power connections on each chip. But let's try this fix with a dual op-amp chip and see how it works. Not perfect, but a little better. Now the final step to design a working standalone metal detector is to ditch the AM radio receiver and build our own heterodyne detector. That detector, or mixer, is simply another operational amplifier. The op-amp has two independent input ports, so we connect them to the output of the two oscillators, each through a resistor to prevent overdriving the mixer. For this part of the circuit, I decided to keep it simple, put these parts on a breadboard panel. Snap Circuit sells these nifty jumper wires, which makes it easy to interface their parts to a breadboard. For the audio amplifier section of the circuit, we have a couple options. The Snap Circuits kit comes with an audio amplifier module and a speaker, which we could use, but I'm feeling a bit lazy, and I want to keep this as simple as I can, so I'm going to use an amplified speaker that's made for a desktop computer. First, let's turn on our speakers, then turn on the oscillator circuit. Let's adjust the tuning capacitor of one of the oscillators and see if we can get them to pair up. Now let's test it as a metal detector. And that, friends, is how it's done. If I were to build this circuit to actually hunt for hidden metal, I would finish out this circuit with a 386 audio amplifier chip and with a speaker or headphones. And I've also provided this schematic in the description of the video. And if you've missed any lessons in this series, I have a link to the full playlist in the description. And thank you for watching. So that one we have to connect over to the negative side. So let's use a clip. Let's use a jumper. Okay.